Okay, today we're gonna discuss about undoing the derectification of a continuous signal and introduce the discrete-time Fourier transform and other properties. So, in the previous lectures on sampling and Shannon theorem, we have seen that given a continuous signal x of t, we can consider the derectified signal x sub s of t, which is equal to x of t times the Dirac train which allow me to sample the continuous signal every t sub s seconds. So ts is the sampling time, sampling period. So we also define the sampling frequency as 2 pi over ts. And we know that when we do this multiplication, the signal that we get is simply given by a bunch of deltas which are sampled every ts seconds. So this is n plus 1 ts, n minus 1 ts, and then here I have my deltas, and in particular the value, and we know that it was easy to show that when I do this multiplication, so when I do x of t times pt, this is equal to x of t times the infinite sum of delta t minus nts. But now I can, because the multiplication is additive, I can swap these two things and get x of t delta t minus nts. But now I apply the sampling property of the delta function, and so the final result is that the derectified signal is given by the sum from n equal minus infinity to infinity of x applied at computed at n times ts times delta t minus nts. And this is my derectified signal. Okay, so that was basically the starting point for introducing the concept of sampling and the Shannon theorem and all the other stuff. Okay, so said that, what we would like to do now is we already compute what is the Fourier transform of the derectified signal. Let's review it. Actually we can rederive it easily. And so we have seen that we have the continuous signal x of t. Here we have the derectified signal x sub s of t. Which now is equal to And of course, what happened here? We see that what we have here is basically what is basically the discrete signal. That we call it x square bracket n, which is equal to the continuous signal sample at NTS. However, no, it is it is embedded into the rectified signal by means of this delta. So the strength of the delta of each delta is basically the discrete signal at time NTS. And actually, after now, I'm going to use this notation, okay? So we call it xn delta NTS. Okay? What we have seen is that if we define the Fourier transform of the continuous signal as capital X of omega, we have seen that this is the Fourier transform. We have seen that the Fourier transform of the rectified signal is given by what? So it's pretty straightforward because the Fourier transform of the rectified signal is equal to the Fourier transform of that infinite sum but the operator is the Fourier transform operator is linear, and so we can swap it. So we have the Fourier transform of xn of t delta t minus nts. Is right? But now this is a constant, and so we can bring it outside. And then we have what? We have the sum over n from minus infinity to infinity of x sub n times the Fourier transform of a delta shifted by nts. But this is equal to e to the minus j omega nts times 1. Okay? So we see that the Fourier transform of this guy, we call it x sub s, is equal to the sum from n equal minus infinity to infinity of x sub n e to the minus j n ts omega. And this form actually remind us of the discrete-time Fourier transform, is right? So indeed, we can, and that's what we're gonna study now. Let's study more in details this spectrum, this spectrum, okay? And introduce the discrete-time Fourier transform. So we see that the Fourier transform of the derectified signal xs of t, which is given by the sum from n equal minus infinity to infinity of the sum of the discrete signal times shifted deltas. We have seen that its Fourier transform is given by n equal minus infinity to infinity of xn e to the minus j omega n ts. And this is if now we define the cyclic frequency omega hat given by omega time ts, we see that omega hat will be less or equal than pi, and this is going to be the principal branch. But we know that this function here is going to be periodic with period omega sub s, is right? Because we also have seen that an alternative form of this Fourier transform is given by the infinite sum of shifted copies of the original Fourier spectrum of the continuous signal x. So, and this was the starting point to introduce the Shannon theorem. Instead, this formulation here is more appropriate to define the discrete-time Fourier transform. Indeed, the discrete Fourier transform, we define it as x sub s of omega hat equal the infinite sum from n equal minus infinity to infinity of the discrete signal times e to the minus j n omega hat. Okay? This is the discrete Fourier dTft of the discrete signal x sub n. That's how we define it. And this is equal to the Fourier transform of the diractified signal x sub s of t. Okay? So here, we have two definitions. So we can look at this quantity as the Fourier transform of the diractified signal, which we also define it as the discrete-time Fourier transform of the discrete signal x sub n. Okay, so it comes naturally, as the Fourier transform of the diractified signal. But now what we would like to do is, given the discrete Fourier transform of a discrete signal, can we recover the discrete signal x bracket n? So how can we define the inverse discrete time Fourier transform? Well, that's going to be the goal of the next few slides. We have our continuous signal x of t, which it is sampled every ts. Now we sample it every ts, and we define the diractified signal x sub s of t. So this is n ts, n plus 1 ts, n minus 1 t sub s. And we have x s of t is equal to x of t times the Dirac train. So we have that x of t is equal to the infinite sum of the discrete signal sample at ts times the bunch of deltas. And we saw that this Fourier transform x sub s, we can rewrite it as the infinite sum from minus infinity to infinity of x of n e to the minus j n omega hat, where we have defined omega hat equal omega times Ts. We have defined the cyclist frequency. And this quantity here is the discrete signal. And xn2s is equal to the continuous signal sample at nts. Okay? So now we would like to, given this, given the discrete time Fourier transform of the discrete signal x of n, which is also the Fourier transform of x of s of t, we, given this, can we recover the discrete signal xn? Well, of course, what we can do now, we can exploit the inverse Fourier transform and derive the original, the Diractified signal. Xs of t, this is equal to 1 over 2 pi, the integral between minus infinity and infinity of x of s of omega e to the plus j omega t in the omega. Okay? So, of course, yes, we can recover this. And here you have to be careful because here I'm using the original frequency omega, and I'm integrating over the entire frequency range of the Fourier transform x sub s, which, as we know, is given by multiple copies of the original spectrum. Is right? So that's what we have seen, by studying the Shannon theorem. Indeed, let's review this this part basically. So we have the Diractified signal, nts, n plus 1 ts, n minus 1 ts. Okay? And this is equal to the infinite sum of a bunch of deltas. And then his Fourier transform, we have seen that in the frequency omega is basically given by 0, omega s, 2 omega s, minus omega s, minus 2 omega s. And so, as long as we don't have aliasing, this is the Fourier transform of the Diractified signal. Which has this representation that follow nicely by taking the Fourier transform of the original signal, but which can also be rewritten as multiple copies, sum of multiple copies of the original spectrum of the continuous signal x of omega, which is this. So of course here we're going to assume that the Nyquist frequency is satisfied, so there is no aliasing. And so we have seen then, we can go back and rewrite the original signal x s of t as 1 over 2 pi, the integral between minus infinity and infinity of xs of omega e to the plus j omega t in the omega, okay? And this is the inverse Fourier transform of xs of omega, which will recover the original signal, the Diractified signal. However, we are interested in recovering the discrete signal, okay? Because we have seen that if we exactly, so we are interested in doing that. So how can we do that? Well, the idea is very simple. We already have these results, okay? This is well established. This is a one-to-one correspondence between these two functions. So we already have seen that we can interpret this as the discrete-time Fourier transform of this signal. Once we match, we define omega times ts as omega hat, and so what we gotta do basically? How can we extract the original? How can we recover the original discrete signal? Okay, just the values at the sampling times. That's what I want to do basically. Okay, I don't care about the entire signal. Well, since here there is the Diractified signal is given by a bunch of is the sum of a bunch of deltas. What I can do is the following. I can define a window which this window, I can recover xn as the convolution between the Diractified signal convolved with a spatial window function, which is going to be defined in such a way to give me the values at the sampling times. So the question is, which window do we choose? Okay. Well, it's pretty straightforward to realize that as long as I have a window that it is 1 at NTS. For example, one of these windows is this. N plus 1/2 TS and N minus 1/2 TS, and then equal to 1. Well, this window does the job, okay? Because I can immediately recover I can sample the value basically at NTS indeed.